124 light years away, there's a planet nearly 9 times the mass of Earth, orbiting a small, cool star, sitting inside what astronomers call the habitable zone, the narrow band of distance where liquid water could exist. And in April of 2025, a team of astronomers pointed the James Webb Space Telescope at that planet's atmosphere and found something that, for a few extraordinary weeks, made headlines around the entire world claim we might have just found the first real evidence of life beyond our solar system. What actually happened afterward, the intense scientific argument that followed, the walkback, the reanalysis, the ongoing disagreement that continues right now in 2026, is a far more honest and in many ways far more fascinating story than the initial headlines led on. This is the real story of K2-18b, what Webb actually detected, why so many scientists are still arguing about what it means, and why the most exciting possible discovery in the history of astronomy still hasn't actually happened, not yet. Let's start with the planet itself, because understanding why K2-18b became the center of this entire debate requires understanding just how tantalizingly close to promising it actually is. K2-18b orbits a small, cool, dim star known as a red dwarf, sitting about 120 to 124 light years from Earth, depending on which team's distance calculation you're using. The planet itself is roughly 6 times the mass of Earth, meaning it's almost certainly not a rocky, Earth-like world in the traditional sense, but something in between our own planet and gas giants like Neptune, a category of world often called a sub-Neptune. Crucially, K2-18b sits within its star's habitable zone, the orbital distance where temperatures could theoretically allow liquid water to exist on or beneath its surface. Some scientists, most prominently Niku Madhusudan at the University of Cambridge, have proposed that K2-18b might belong to a theorized category of planet called a Hycean world, a planet with a deep, global ocean sitting beneath a thick, hydrogen-rich atmosphere. If that description is accurate, and it's important to stress that it remains a hypothesis rather than a confirmed fact, K2-18b could represent an entirely new category of potentially habitable world, different from anything in our own solar system, but potentially far more common across the galaxy than small, rocky, Earth-like planets are. The story of Webb's involvement with this planet actually started back in 2023, well before the headlines that would eventually explode 2 years later. Madhusudan and his colleagues used 2 of Webb's instruments, the near-infrared imager and slitless spectrograph, known as NIRISS, and the near-infrared spectrograph, known as NIR-SPEC, to study K2-18b's atmosphere as it passed in front of its star, a technique called transmission spectroscopy that lets starlight filter directly through a planet's atmosphere on its way to our telescopes, carrying with it the specific chemical fingerprint of whatever gases are present. That 2023 study, published in the Astrophysical Journal Letters, confirmed the presence of methane and carbon dioxide in the planet's atmosphere with strong statistical confidence. Methane detected at a confidence level astronomers call 5 sigma, essentially about as certain as science gets, and carbon dioxide at a slightly lower but still meaningful 3 sigma confidence. Buried within that same 2023 paper was something else, though, mentioned with far more caution. A lower confidence hint of a molecule called dimethyl sulfide, or DMS. That molecule is the entire reason this story became as explosive as it did. On Earth, dimethyl sulfide is produced almost exclusively by biological processes, primarily marine phytoplankton, tiny ocean organisms that release the compound as part of their normal biological activity. It's one of a small handful of molecules that scientists have specifically flagged as a potential biosignature, meaning a chemical that, if detected in sufficient quantity on another world, could indicate the presence of biological life, because we don't currently know of any efficient, large-scale way to produce it through purely non-biological chemistry, at least not here on Earth. Finding a confirmed, strong signal of DMS in the atmosphere of a distant exoplanet would be, without exaggeration, one of the most significant scientific discoveries in human history. That 2023 hint wasn't strong enough to claim anything close to that, but it was tantalizing enough that Madhusudan's team went back for more, this time in April of 2025, using Webb's mid-infrared instrument, known as MIRI, to observe K2-18b's atmosphere across a different range of wavelengths, roughly 6 to 12 micrometers, specifically chosen because that range should show a clearer, more distinct signature of DMS if it was genuinely present in meaningful quantities. When that data came back, the team reported that the observed spectrum statistically preferred the presence of DMS or a related compound called dimethyl disulfide, DMDS, at approximately 3 sigma confidence, roughly the same statistical strength as their original carbon dioxide detection 2 years earlier. And this is where the story exploded into public awareness, and where, in retrospect, a lot of the coverage ran ahead of what the actual data supported. Headlines throughout April of 2025 described Webb detecting signs of life. describing K2-18b as the most promising candidate yet for a confirmed biosignature beyond our solar system. Some outlets, and plenty of social media commentary, went even further, framing the discovery in language that implied confirmed alien life had essentially been found. NASA itself, notably, remained far more measured. In a statement given at the time, the agency was explicit that detecting gases produced only by life is genuinely difficult using Webb, and requires extremely long observation times to build sufficient statistical confidence. Even in the best case, NASA stated plainly, detection of a single potential biosignature would not, on its own, constitute discovery of life. That's an important, carefully worded distinction, and it's the exact distinction that got lost in a lot of the more excited coverage that followed. Sarah Seeger, an astrophysicist widely respected in the exoplanet research community, offered some of the most important context on why this specific kind of claim deserves real scrutiny. She pointed out that for nearly 100 years, astronomers have wrestled with a particular logical trap, identifying a gas in a planet's atmosphere that seems chemically unstable or reactive enough that it shouldn't persist without something actively replenishing it, and then reasoning that biology must be that something. That style of reasoning traces back to physicist James Jeans in 1930, who first used exactly this logic when he identified oxygen in Earth's own atmosphere as a marker worth flagging, and used similar reasoning to place theoretical limits on how much oxygen could plausibly exist in Venus's atmosphere. Seeger's warning, delivered directly in the context of the K2-18b debate, was blunt. With thousands of exoplanets now being studied, the temptation to overinterpret ambiguous data is strong, and some researchers, in her assessment, were jumping the gun. She went further, predicting that this particular finding would likely remain permanently stuck in what she called the candidate category, a plausible signal worth continued investigation, but never quite strong enough, at least with current data, to cross into confirmed discovery. That skepticism turned out to be well-founded, and the story took a genuinely important turn as more of the scientific community weighed in during 2025 and into 2026. Independent research teams began re-examining the same Webb data using different statistical methods and different assumptions about the planet's atmospheric chemistry, and the picture that emerged was far messier than the original headlines suggested. Some competing analyses found that the specific spectral features attributed to DMS and DMDS could potentially be explained by other, entirely non-biological molecules and chemical processes, meaning the debate wasn't only about whether finding those specific gases would prove life. It went one crucial step further back, whether the data even required invoking those gases at all to explain what Webb had actually observed. A survey of practicing astrobiologists, published in the journal Nature Astronomy, captured just how unsettled the scientific consensus really was. When directly asked whether they agreed that Webb had found convincing evidence of DMS or DMDS on K2-18b, only about 6% of the astrobiologists surveyed agreed. Not a slim majority, not a contested plurality, barely 1 in 15. As of where things stand now in 2026, the honest, sober scientific summary is this: the evidence available does not support saying that Webb found life on K2-18b, and it doesn't even securely establish that DMS or DMDS are actually present in its atmosphere at all. What Webb did confirm, with genuine strong statistical confidence, is that K2-18b has a real, substantial atmosphere containing methane and carbon dioxide, itself a remarkable technical achievement for a planet this small and this distant. The presence of a potential biosignature gas remains exactly that, a candidate, an intriguing possibility supported by data that different, equally qualified teams of scientists interpret in meaningfully different ways. This is, in its own way, exactly what real scientific progress is supposed to look like, even though it makes for a messier story than a clean, triumphant headline. NASA's own public materials on this topic lay out, with real clarity, just how difficult the search for genuine biosignatures actually is. Detecting a gas convincingly enough to build a real case for biological origin can require hundreds of hours of dedicated observing time focused on a single planet. And even then, results frequently remain ambiguous because both the host star and the planet's own atmosphere continue evolving and changing over time in ways that complicate clean interpretation. NASA has stressed, explicitly and repeatedly, that a single potential biosignature detection would never, on its own, constitute an actual discovery of life. Confirming something that significant would require multiple independent lines of converging evidence, ideally gathered using more than one instrument or mission, along with extensive atmospheric modeling specifically designed to rule out every plausible non-biological explanation, before a genuine claim could be responsibly made. That's the part of this story that deserves real attention, arguably even more than the initial exciting headline did. We are right now in 2026, living through the earliest working stages of a genuinely new scientific capability. the ability to point a telescope at the atmosphere of a planet orbiting another star entirely, and actually determine what that atmosphere is chemically made of. That capability simply didn't exist in any meaningful, precise way before the James Webb Space Telescope came online. K2-18b, becoming the most argued over exoplanet of 2025, isn't evidence that the search for life beyond Earth is failing. It's evidence that the search has finally become precise enough to produce genuinely contestable, genuinely meaningful scientific disagreement. The kind of disagreement that only happens when the underlying data is actually good enough to fight over in the first place. Nobody involved in this debate, on any side of it, is claiming the search is over, or that K2-18b has been ruled out as a genuinely interesting, potentially habitable world. Follow-up observations are already planned and, in some cases, already underway, using longer exposure times, different instrument combinations, and more sophisticated statistical models, specifically designed to either strengthen or definitively rule out the original DMS signal. That's exactly the process NASA itself has said would be required before anyone could respectably move this finding out of the candidate category and into confirmed discovery. Whether K2-18b ultimately turns out to be a genuinely habitable, possibly even inhabited ocean world, or simply a fascinating, chemically rich sub-Neptune with an atmosphere that happened to produce an ambiguous, ultimately non-biological spectral signature, remains a genuinely open question that current data cannot yet answer with confidence. What we can say, honestly and without exaggeration, is this. For the first time in the history of astronomy, we have an instrument capable of asking this exact question, in this much specific chemical detail, about a planet we will never visit, orbiting a star more than 100 light-years away. That alone represents a genuine turning point. The answer, whatever it eventually turns out to be, is still being written, one carefully contested observation at a time.